concavity and convexity of functions. Well, for a function to be concave or convex, now its domain of definition that has to be a convex set. So we will quickly review some very basic properties concerning convex sets. As you know, a set is convex if and only if for any 2 points xy in the set and for any lambda in the unit interval, lambda x plus 1 minus lambda y belongs to the set again. But there we have addition of vectors, lambda x plus 1 minus lambda y, and scalar multiplication. So actually, the most general mathematical construct where convexity makes sense, that's the notion of a real vector space. So we'll actually define our functions also on subsets of real vector spaces, unless we will refer to continuity, differentiability, and so on. So let's start right away with the definition. Let V be a real vector space and xy 2 points in the real vector space. Now in Rn, in Euclidean spaces, we had defined the notion of segments, line segments. Well, here I'll do that, unfortunately, once more, but in the context of a real vector space now. We define xy as lambda x plus 1 minus lambda y, such that lambda is in 0, 1. xy lambda x plus 1 minus lambda y, such that lambda is in the open interval 0, 1. Then x included, y excluded. This will be lambda x plus 1 minus lambda y, such that lambda is 0, 1, because it is 1, which corresponds to x here. That should be included. Lambda equals 0, that corresponds to y, that's excluded. Finally, xy lambda x plus 1 minus lambda y, such that lambda is this time in 0 included, 1 excluded in the unit interval. Now, as we have noted, well, if x and y are equal to each other, these three sets, they do not turn out to be empty, but they turn out to be just a singleton. Because if you take just lambda equal to 1/2, 1/2 x plus 1/2 x, well, that's x, so well, that's the difference from the interval notation in R. But that was the case also for line segments in Rn, okay? Now, let A be a subset of V. A is set to be convex if for all xy in A, the segment xy that's entirely contained in A. Next, let x1 up to xk be points in A, and lambda 1, lambda k points in the unit interval with their sum I from 1 to k being equal to 1. We refer to y equal to the sum of lambda I xk's from 1 to k as a convex combination of x1 up to xk. Moreover, we denote C of A for the set of all convex combinations of finitely many members of A. Now, the simplest proposition of the course let V be a real vector space and A be subsets of V. 1, A is contained in C of A. Well, because if you take any member X from cap A, that's finitely many. It has only one convex combination, 1 times X. That has to belong to C of A. X belongs to C of A. Secondly, if A is contained in B, this implies that CA is contained in CB, because any collection of finitely many members of cap A is also a finite non-empty collection in B. Thus, we have this. 3, A is convex if and only if A is equal to C of A. One direction of this is obvious. If A is equal to C of A, then you take 2 points from cap A at a time. Well, any convex combination of them is in CA, but if CA is equal to A, then the entire segment, lambda x plus 1 minus lambda y, for each lambda in the unit interval, since it's in here, it will be in here. Well, the other direction, that's a bit more involved, but it's easy as well. Fourthly, C of A, that's equal to C of A, that is C of A is convex. Well, because if you take finitely many members from C of A, well, then each of them is a convex combination of finitely many members from cap A. But if you take any convex combination of those finitely many members, C of A, well, the combination of the two facts, well, that yields another convex combination of finitely many members from cap A. Because one direction, according to this, C of A, that's already contained in C of A, but the converse also holds. So all this is left as an exercise to you. Next, again, a very simple proposition. Let I be a non-empty set and well, let me take again V as a real vector space. Let V be a real vector space and A alpha a convex subset of V for each alpha in I. Now, if we take the intersection of all of them, this will be convex as well. Well, although the proof is again simple, let's this time go through it. Assume that, of course, the empty set is convex because the condition is for any xy in the set, any convex combination of them should belong to the set as well. Well, if a set contains no members xy, then whatever follows for all xy in the empty set, whatever the scope of that is, whatever follows that, that will trivially become a true statement. Assume that xy, they belong to this intersection. So that's why I'm not saying let xy in here, because if I say let xy in here, then I have the responsibility of showing that there are such xy. But here, assume that this, well, if this is empty, this will be a false statement. Whatever follows, the false statement implying any statement, that will be true as well. Now, x and y separately are in A alpha for each alpha in I. But since each A sub alpha is convex for each alpha in I again, the line segment xy, that will belong to A alpha since A alpha is convex. But then this is a subset of each of these A alphas, so it is also a subset of their intersection. Thus, this intersection is convex. But this makes the definition of an important notion possible. Well, suppose you start with a set in a real vector space V, which may or may not be convex, but you might be, in case it's not convex, you might be interested in the smallest subset of V, if any, which is convex and contains the given set. So according to this fact, we can define it as follows. Let, again, V be a real vector space and A any subset of V. The convex hull, which we denote by Koray, of A is defined by now we will take the intersection of all subsets of V, C, such that C contains A and C is convex. Now, will this intersection contain A? Yes. Each set in the collection over which the intersection is taken contains A, thus the intersection contains A. Will it be convex? Yes, this is now a whole bunch of a collection of convex sets. Well, but then their intersection is convex again. So this is a convex set which contains cap A. Is it the smallest such set with respect to inclusion? Yes, suppose you have some C prime which is convex and contains A. Well, then that C prime belongs to this collection. Thus the intersection over this collection will be contained in C prime. The C prime will be a convex set which contains the convex hull of A. So this is just like the closure of A. Well, there the definition was different, but it turned out you start with some set A in a topological space. You consider all closed sets which contain A. You take the intersection of them, but the intersection of any bunch of closed sets is closed. So that intersection turns out to be closed as well as it contains A. And it was the smallest closed set containing A with respect to inclusion. If A itself was closed, then its closure was equal to itself. Here again, if A is convex, then the convex hull of A, that will turn out to be itself, because A will be a member of this collection over which the intersection is taken. Everything is a superset of A, so the intersection will be equal to A. Now here we have two ways of producing a convex set from a given set A. One is forming this CA, and the other is forming this convex hull of A. Here, we actually, in defining this, we resorted to a constructive means. We know how the members of C of A are constructed from the members of cap A. Here, that's not existent in this definition. Okay? It's like synthetic geometry and analytic geometry, if you wish to put it like that. But now we have the following proposition. Let V, again, be a real vector space and A a subset of V. Now, convex hull of A is equal to C of A. The proof is simple. Well, since this is a set equality, we need to show inclusions in both directions. Now, first, note that A is contained in C of A. But by definition of the convex hull, this means that convex hull of A is contained in the convex hull of C of A. But what do we know about this? What do we know about C of A? That's convex. But the convex hull of a convex set is just itself by definition. Since C of A is convex. Thus, convex hull of A is contained in C of A. Well, let me write that as well. Convex hull of A is contained in C of A. But now, let's do the same thing, but the other way around. Instead of starting with A and C of A, let's start with A and convex hull of A. A is in the convex hull, because this is the smallest convex set containing A. But that implies that C of A is contained in C of convex hull of A. But what do we know? C of a convex set, that's just itself. This, since convex hull of A is convex. So C of A, that's contained in convex hull of A as well. Therefore, we have equality between the two. Although this notion is simple and familiar to you, now let's see some examples for the sake of completeness. Now let V together with this be a normed space. Let R be a positive real number. Set A equal to the set of all x in V such that the norm of x is less than or equal to R. Is this a convex set in V? Let's check. Take any xy in A. This time I can take any xy in cap A because this will be non-empty. Why? Can you tell me one member of this set, at least, in cap A? Well, this is a real vector space. It has a zero vector, and the normal to zero vector is 0. And lambda in 0, 1. Well, since x and y are in here, the norm of x, that's less than or equal to r, so also is the norm of y. Is lambda x plus 1 minus lambda y in here? Well, it's in V. Because these are binary operations on V. The sum of any two vectors is a vector in the set, and the scalar product of any vector, that's again in the set, with, now we need to check whether this will be less than or equal to R. But since this is a normed space, the triangle inequality that holds but since it's a normed space, we know what happens to the norm of a scalar product. This is equal to the absolute value of lambda, the norm of x, plus the absolute value of 1 minus lambda, the norm of y. But lambda and 1 minus lambda, since lambda is in the unit interval, they're both non-negative. Lambda x plus 1 minus lambda y. But this now is less than or equal to the first term, lambda times r, since this is less than or equal to r and this is non-negative, plus 1 minus lambda, and this is less than or equal to 1 minus lambda times r, but that's equal to r. So A is convex. This is example 1. Now example 2, that's one of the most famous convex sets in economic theory, which will be the example here. Now write RL plus for the set of all L vectors which are non-negative. Now let P and omega be two members of RL plus. We sometimes take P in RL plus plus such that all components are positive. Set P omega equal to the set of all x in RL plus such that P dot x is less than or equal to P dot omega. What's this set? It's the budget set. And that's convex. And the convexity of the budget set that actually enters almost all theorems in general equilibrium theory. Now check that, I will leave it to you, it's clear. Check that P omega is convex. Okay, so much about convex sets for the time being. Now let's pass to concave and convex functions